This is going to be the review session for the Chapter 3 stoichiometry test. Now, bear in mind, I've already put this in the email. We're going to take both parts tomorrow, the multiple choice and the free response. You can correct me if I'm wrong, but the multiple choice is 23 questions. Is that what I said?
Yeah.
Yes, 23. The free response is, I can look at it, but it's, I can look at it. If you'll give me just a second, it's in here somewhere. Yes. It's somewhere. I'll tell you what, it's going to be number 1, A, B, and C. Number 2, A, and then it's going to have I, double I, triple I, quadruple I, and B, I, and double I. But you have to remember, prime example, quadruple I is determine the empirical formula. That should take you about 2 minutes at most. It should take you about 2 minutes at most. Okay? And then B, single I, I'll go ahead and tell you, I'm not going to tell you the data, but it says the molar mass of the compound. You should know how to do that. Okay? You should know how to do that. And then double I is the molecular formula. So you take the empirical, convert it to from the molecular. All right? So a lot of this will go pretty quick. And then question 3 is A, B, I, B, double I, and C. Again, very quick, won't take long. All right, so let's look at 2003B. Answer the following questions that relate to chemical reactions, and it says iron 3 oxide can be reduced. Now let's talk about this word right here. We're going to kind of get into this later, but when it says reduced, do me a little favor. Please write oil rig, and then above oil rig, write oxidation state. Because I'm going to throw in just a little bit of electrochem just to kind of throw it at you for just a second. It should be pretty simple. Remember, reduced. What does oil rig mean? Oil is oxidation is a loss. Yes. Reduction is a gain. Okay. So what we're going to do is we're going to reduce the iron 3 oxide with carbon monoxide. Okay, and we'll just kind of get in there. And what it's talking about is oxidation states. Real quick, just throwing this at you. If I were to find the oxidation state of this, do you agree that oxygen is always -2? Remember that? Bring the math down. What's that going to bring the math down to be? -6. So what's the only thing to make that true? +6. And so what's the oxidation state of iron specifically? +3. So you'd agree the oxidation state of iron is +3 right there? You should all know how to do that. Yes? What is the oxidation state of something by itself?
Pure 0.
0. So do you agree that iron was reduced?
Yeah.
What did it go from and to?
0.
3 plus to 0. That's reduced. That's a fact of chemistry. Okay? Just want to throw that at you. So then they give you the reaction. Good job. It's balanced. We don't have to do anything with it. And then they give you this information. A 16.2 liter sample of CO, which is carbon monoxide, at 1.5 atmospheres. So let's talk about the two things they've given you. What is L a unit of? Volume. So they've given you a volume. ATM, what is that a unit of? Pressure. And they've also given you a Celsius, which is that's interesting, a volume, a pressure, and a temperature. What do you think's probably going to have to happen there? More than likely, we're probably going to have to use Pivner potentially in this question. Just kind of throwing that at you. Now, do you agree that everything they've given you so far has just been for one particular compound? It's been just for carbon monoxide, right? Then they flip gears and they change it on you. And they tell you you have 15.39 grams of that iron 2 oxide. Okay? You agree right there? Question 1. How many moles of carbon monoxide are available for this reaction? So the specific question they're asking for, do you agree, is moles of CO? What pieces of data are you going to use for this question? The things that are attached to CO. What are the 3 pieces of data that are attached to CO? The volume, the pressure, and the temperature. We've already established that we're probably going to have to do PivNert. Do you agree? So we're going to be searching, and this is where I'm going to start doing my work. We're going to be searching for the N of CO. Do you all agree with that? Okay? We're searching for N. What does N stand for? Moles. If I take PivNert and rearrange it, try to do it in your head. Does anybody know what it will be in your head? Very good. PV over RT. Okay, that's what it's going to equal. Just algebraically rearranging that thing. All right, what was the pressure they gave us? 1 point what? 5 ATMs. What was the volume they gave us? 15 or something? No? 16.2 liters. Here's the very special one. That's R. Which R, gas or energy? Gas R. And the numerical value? 0.0821. That, now remember, it's not going to be given in the question, but consult your formula sheet. Okay? Does that make sense? Consult your formula sheet. Liters times atmospheres, so it's liters per mole, or atom over mole. And then finally, there's something different about our temperature. What's wrong with the temperature? It's in Celsius, and you must convert it to Kelvin. How do you do that? Add 273, which makes it, what, 473? Is that right? Okay, 473 Kelvin. Now, do you agree that all of your units but which one will cancel? So atmospheres cancel, liters cancel, Kelvins cancel. Now, I'm just going to show you this because I want to make sure you understand what's going on. Do you all agree that moles is on the bottom in the bottom? Let me say that one more time. Moles is on the bottom in the bottom. So essentially it's 1 over moles. How do we just get moles out of that thing? This is basic algebra. Anytime you have a fraction in the bottom, you multiply by the reciprocal. So this is going to equal 1 times mole over 1. Is that not the exact same thing? What's going to happen to the ones? Leaving you with just... So do you have to show that? No. Just write moles and put your answer down. Okay? Due to time's sake, I want to give you the answer. The answer to this will be... Let me find it on here. Sorry. That's the wrong page. That's why I can't find it. Is right. The answer to this is going to be 0.626 moles of CO. That's your answer. Could you have gotten that answer? They asked you for moles of CO. They gave you pressure, volume, and temperature. You should be able to calculate the moles from that. Yes, sir. Always do sig figs. Forever and forever and ever and ever and ever. Let me show you how this is going to work. In AP, just to show you guys, this is how you'll write your answers. It'll be on line paper. So you'll work everything out like this. And this is what you'll actually see the day of the exam as well. Yeah, you'll just circle it. Okay. Actually, they've kind of gotten away from circles, and here's the reason why. Me circling this tells me what? That is the answer. You are locking yourself in. Sometimes they actually say it's better not to circle the answer because let's pretend that you're like, I have no idea what to do, and you do a whole bunch of work, and for some reason you plop the answer down and you do something else somewhere else. They may just take that answer because you have it written down. So they're kind of saying, be careful with your circles unless you're certain.
It's like your circuit went both which way to do it, and you get it both ways, and one of them is right.
Now they can figure that out. It's kind of like you wronged your right. Does that make sense? You wronged your right. So to be honest with you, I've never actually graded the real AP exam, and so I don't know how they do that. That's kind of one of those weird situations. All right, so that's that part. That is A. So let's move on to the next one. That was I. Now part double I. What is the, and this is the key word, and I've been begging you guys forever to be able to make sure you understand this. Which one is the limiting reactant? Now, do you agree that we have 0.6, was it 626 or 636? 626 moles of this, and we're originally starting with 15.39 grams of this. Can you compare those two numbers as is right now? Why not? Okay, the only way you can compare two different things is moles. Now, how did you even know that you were going to have to solve for this? Okay, remember, do you have two reactants? Do both of them have a starting amount? You're going to have to find a limiting reactant. There is a cheat for this. Remember, the cheat is limiting reactant is moles divided by the coefficient. This is only used as an identifier. What does it mean to be an identifier? You just know what it is. It's no mathematical help in stoichiometry. It's just going to show me what it is. Now, the LR, well, let's check this. Let's do this a little bit different. All right, so we're going to do CO because we have it. 0.626 moles. What is the coefficient on the CO? Look back at the balanced equation. 3. Somebody plug that in for me real quick. Okay, all right, so that's that answer. And then it's the mass of iron 3 oxide was 15 point what? 39 grams. What's the first problem with that right there? It's in grams. Let's get it to moles. I'm going to let you guys do this, but I'm going to give you the molar mass. 159.7 grams is 1 mole. Determine how many moles that is. Side note, real quick, just a minute ago. Guess how many points you earned for doing PivNert? 2 points. You earn 1 point for just plugging numbers in and 1 point for the answer. You've earned 2 points out of 10 for just plugging in numbers into PivNert. Okay. All right. What was the number of moles for this that you got? Very good. 0.964 moles. Now, what's the coefficient for this one? And the balanced equation? It's 1. So, isn't it not the exact same answer? So, based on this, what's your limiting reactant? Very good. Since this is the least, then that means this is the what? It's your LR. Yes, ma'am. You can do that as well. That's perfectly fine. All right, what she just said, guys, is, as a matter of fact, you don't even have to convert it to a product. You can convert them to each other. Basically, you would pick one and convert it to the other, is how you could do it. Okay. Essentially, to be honest with you, if you want to think about it like this. All right, just follow the blue for just a second. 0.626 moles of CO. You with me? Okay. I want to go from moles of CO to moles of Fe2O3. Do you agree that all I'm doing right there is converting CO to Fe2O3? What would be my top to bottom mole to mole ratio right there? Does this and that look real similar? It's the exact same thing. The exact same thing. So you're going to get the same answer here. So once I have the moles of iron 3 oxide, doing this, it's going to be the exact same answer. Did everybody see what I just did? Okay. One more second. One more time. Ignore the black for just a second. What I did is I'm comparing carbon monoxide, correct, to the other reactant. What was the other reactant? Let's change that color. Fe2O3. All I did was a mole-to-mole relationship, right? Does this blue mathematically not match exactly what I did in black? So the answer would be identical. So essentially, you're really doing the same thing. Just do it a little bit differently. It's going to give you the same answer. Yes, sir?
I thought to find the limiting reactant, you had to take both products, or both reactants, and convert them to the same product.
All right, let's try that. Pick one of the reactants. Pick any of them.
Fe.
Why Fe?
Because it's
All right, it's the smallest. So if I convert this to 2, okay. All right, this time I'm just going straight to Fe. Now, Alex, do me a favor. Multiply 6.26 times 2 divided by 3. Or, tell you what, easier, double that right there. Just double 2.09, or 0.209. 0. What? Okay. All right, now, I have moles of this thing, okay? And 1 mole of Fe2O3. Do you agree it's still going to be 2? Okay. It's still going to be 2 moles of Fe. Double that number and tell me what you get. Point what? Which one is still least? Still least. It's still your limiting reactant. No matter how you do it, as long as you're comparing moles to moles, it's still going to work. You can compare them to each other, or you can compare them to a product, because the mole to mole ratios are always going to work the same. Does that make sense? We've done it 3 ways, and all 3 ways we've got the exact same answer in terms of the limiting reactant. Okay, and that's a difference, but it's okay. It doesn't matter how you do it. All 3 ways work. You do with what's comfortable to you. Okay. The last thing that I want to make note of: do you agree that we've determined the limiting reactant? This year, I want to take it one more step, and I also want to make sure that we identify the excess reactant. Just make sure you write ER, so if they talk about it, you can go back and determine it. Okay? Just make sure you can compare it. All right, so here's the numbers that I'm going to use for just 1 second. I'm going to erase all this other stuff except the numbers I need to use. Do you all agree that we've determined that this bottom thing is the limiting reactant? By our simple definition, what do we always say about our limiting reactant? It runs out first, which means it's going to end up being what numerically at the very end? So this number is essentially going to turn into 0, correct? Here's a simple way to do this. What if the question now was, how much excess remained? Isn't this how much you're starting with? Aren't you going to use exactly that much? Subtract it. That's how much will be left. Okay? That's a totally separate side note for later on unless you want to do it. Okay? But that's what you could do. All right. So let's get back into the problem. So we've identified it. So what is the answer to the question in part 2? What is the limiting reactant? That right there is your answer. But keep reading. Notice what they say. Justify your answer with what? Have we done that? You've earned 2 points.
So you just guess, you get a point. Like if you guess, like if you just wrote Fe2O3, you get a point.
Not with this new redesign. Nowadays, the way they would do it, it would be 2 points with correct answer with correct justification. Does that make sense?
So it's either all 2.
It's all 2 or all or nothing is the way they've redesigned it. And that's why the test has gotten a little bit harder, is they've combined points where they used to split points. Okay? All right. Now, here's the question. how many moles of Fe are formed in the reaction. So now what we're trying to do is we're trying to go from some data about the reactants, and they're asking a specific question about the products. Which one do I pick? The limiting reactant. Fantastic. The moles of the limiting reactant was what? 0.09 something. Thank you. 64 moles of Fe. Thank you. How simple is this question? We're going from what to what? Mole to mole. That is a one-step, wham, bam, thank you, ma'am problem. And it's a 1 to 2. You never heard that? Wham, bam, thank you, ma'am?
No.
You've been living under a rock.
You've been living
I mean, I'm like 46. I'm old as dirt, guys. Dude, I'll be 27 next Wednesday. My birthday is a week from today. No, we're not going to have a birthday party. So, again, real simple, straightforward. So, Matt, do you feel smarter now that you've been able to figure out this answer?
Yes.
Yes.
So bad. Like, I stopped doing that so I could put it.
Okay. All right, so let's move on to part B. Now, I want you to notice something. In the first question, do you agree they have given you the reaction? When you get to B, have things changed? They have given you a brand new reaction, have they not? As soon as they change the reactants and products, you need to completely forget everything above it. Pay no more attention to it, because essentially it's like a brand new problem. It's like question 2. We're moving on to something completely separate. So let's see what they're going to ask. All right. In a reaction vessel, 0.6 moles of barium nitrate and 0.3 moles of, what's this thing right here? It starts with an H and it's aqueous. What polyatomic is PO4? Phosphate, and 8 turns to ic, so it's phosphoric acid. So barium nitrate, phosphoric acid are combined with deionized water. Now, why does it matter we're mixing it with water? That's okay, because all acids must be in water. To a final volume of 2 liters. The reaction represented below occurs. So we have barium nitrate plus phosphoric acid yields barium phosphate plus nitric acid. I want to point something out to you. What type of reaction is this specifically? What?
No, a double replacement.
It's a specific type of double replacement. Number 1, why is it not an acid-base reaction? There's no base. However, we want to add something a little bit new to our knowledge base. This reaction is called a precipitate reaction. For what reason? A solid formed. Notice what you had. What were the states of matter as of the reactants? You had 2 liquidy things. Liquidy. 2 liquidy things. You pour them together and a solid forms. Now, am I talking about like a brick? No, I'm talking about like pieces of particles. It's like basically like coffee grinds, if you will. If you pour the product through a coffee filter, you could collect it. I'm not talking about something that turns into a solid piece of rock, okay? I'm talking about little pieces of particles that are going to form together. Calculate the mass of that compound that is formed. Where do you think we begin? Well, they have given us 0.6 moles of this stuff and 0.3 moles of this stuff. Which one do I pick? The LR, very good. How do we find that thing? Do you already have it? No. This is a brand new reaction. Brand new. Okay. So, again, the LR is equal to moles divided by the coefficient. This is our identifier. This is going to help us get started. So 0.6 divided by 3 is, come on, math geniuses. 0.02 or 0.2? You're right, it is 0.2. My bad. What am I thinking? 0.6 divided by... Yep, I know. My bad. It's been a long day, guys. It has been a long day. 0.2. And the other one, 0.3 divided by 2, is 0.15. So, based on that, which one's your limiting reactant? The one with a 0.5. So, which would be what? Phosphoric acid. Our phosphoric acid is going to be our limiting reactant. So now, go ahead, Alex.
Wait, how do you know the moles of all this?
Wow, buddy. Wow, buddy.
I'm just confused. I'm like,
All right. No. This is why we're here. This isn't class. This is review. This is the time to stop me. Alex, stop me. No. I want you. This is why you're here. Don't think that this is like class and you can't stop me. This is why we're doing this. Let me ask Alex. Ask his first. You got it? Do you know where those numbers came from?
the words.
Okay. Matt?
Alright. Me and Chandler, we were kind of confused. Like,
Okay.
just like let's just calculate the mass, like just do VA, like find on the periodic table.
Okay.
And then like multiply by times 3 and then add them all together.
Okay.
To get like the mass. Like the
Okay.
like,
All right, that's the molar mass. We're talking about when I take 6 moles of this stuff and 3 moles of this stuff, and when I pour them together, I'm going to create a 2-liter bottle full of this stuff. Okay? And when I take that 2-liter bottle and I pour it through a coffee filter, how much of the solid would have showed up? What you're talking about is taking the molar mass of that thing and saying it's going to be that many grams. You can't do that because you've got to base it upon the moles of this stuff. Just like if we were going to cook burgers this weekend. I don't know how many burgers I'm going to cook unless I know how many pounds of meat I have and how many buns I have. Does that make sense? So you can't just automatically jump right into it. You've got to determine how much you're starting with. Like, I would love to cook burgers for everybody, but if I only go buy a pound of hamburger meat, you're not going to get a very big burger. Does that make sense?
Yeah.
Okay. Yes, sir.
So you're gonna use the gram.
All right, so what we're now going to do is you've all done this 100 times for me. You've gone from moles of this, and what are you going to do? Go to grams of the barium phosphate. Set it up, and I will give you the molar mass of, you only need the molar mass of one of them, correct? What's the molar mass you need? Which one? All right, the molar mass of barium phosphate is, if I can find it, can't even find it on here. There it is. Okay. It's 602 grams. 602 grams. Matt, the only way to do what you were asking is just you saying find that number and say that would be the answer, is if we had exactly 1 mole of that stuff produced.
So if it wanted to do that, so it would say calculate the molar mass.
Exactly.
So if it just says mass.
Do what?
It just says mass, so we're not going to.
You're specifically talking about grams.
Okay.
Can you show me what stuff we just said? Yeah.
All right. That's fine. Whoa, hold on.
Wait, what?
Okay, now that makes more sense now. They did it 2 ways, and I'm going to show it to you in just a second. They confused me with their answer, but it makes more sense. Sorry. What is the mole-to-mole ratio between phosphoric acid and barium phosphate?
2 to 1.
Top to bottom?
1 to 2. I'll say it like this.
No, that's fine. My bad. Guys, y'all are making this a lot harder than it really is. No, I get that it is your first test. However, you have been doing grams to moles since November of last year. You did this all summer. Yeah, right. Yeah, that's exactly what you did, considering I did videos that you didn't watch.
Oh, God. Once again, I'm sorry for that.
All right, again, what we have done, let me start over. The first thing we did, my first question is, why did I have to find the limiting reactant before I ever began? Why did I need the limiting reactant? Okay, well, here's the thing. I didn't know which one to pick from. They gave me a starting amount of each one. So do I pick the barium nitrate or do I pick the phosphoric acid? You pick the one that's the limiting reactant, the one that's going to basically least produce the amount. Well, once I know the limiting reactant, again, the purple numbers have no resonance in my math. It's just an identifier. Then you go back to the original amount. So I'm going from moles, 0.3 moles, all the way to grams. You've done this 100 times. It's just a little bit different than you're used to seeing it. You're letting AP scare you when you've done problems just like this in honors. You're letting it scare you. Okay, so if you've done this correctly, you should get 120 grams of barium phosphate. Did anybody calculate and get that right? Good job. Way to go. What's wrong, Alex?
I got 90.3.
Alex, did you give me the wrong thing? Hang on. Whoa. Here's what it was.
I didn't do that.
It's impossible. 0.3. That's I look. Can I show you? Let me just show you why I wrote that down. Hang on. No, you're right. The answer is 90.3. Let me show you why I messed it up. I'm looking at the key, and let me show you what they did. Let me.
When we're doing it down the street, like pointing back what it is. I hate when it is.
All right, let me show you why. Nope, that's the wrong one. Is this it? Yeah, this is it. I think. Is this question world? No.
Are we on the answer thing that says instead of school?
No.
You get paid extra to grade AP Chem test?
You can, yeah. All right, here's their answer. All right, so here's the question. I just want you to pay attention for just a second, okay? What they did is they determined, and I'm just going to show you this part of it. H3PO4 is the limiting reactant. Okay, we've already determined that. Notice what they did. They took the moles of phosphoric acid. They went mole to mole. Do you agree? And then they went mole to gram, and there was the answer. Exactly what you calculated. Here's where I got my number from. If you keep reading, it says if barium nitrate is used as the limiting reactant. So let's say you pick that one. Notice they went mole to mole and then mole to gram, and that's where I came up with 120. I read the sheet wrong, so my apologies. That's where that 120 came from. You're right if you got 90.3. But if you pick barium nitrate, you still could have earned a point. You still could have earned a point. If your math proved that barium nitrate was the limiting reactant, you still could have earned that point, even though technically you were kind of wrong.
There's a way to prove that that was a limiting reactant?
Your math would have to be completely messed up. Yep. Here's what you would not have gotten was if you would have not gotten the 1 point for the limiting reactant. That would have been wrong. But let's say that for some reason, somehow you did come up with the limiting reactant of barium nitrate. As long as you did this part correctly, you would have gotten that 1 point. Does that make sense?
Wait, Mr. I thought you said all of them.
Not on every question.
Not on every question.
Are we going to be able to use your calculator?
Yes. Yeah, absolutely. Yeah, absolutely. Yes, sir.
What did we just solve for?
We solved for the mass of barium phosphate.
Yeah, that was formed, right?
That was what? Yeah, that was formed.
But I thought
Say it again. I can hear you.
I thought the 602 was the
602.
602.
That's the mole. Okay, hang on. Yeah. Well, no, this is right. That's the molar mass of that compound.
Versus
This is the answer. Sorry, that's actually not the answer. It was 90.3. I mean, it's just a mole to gram conversion. Does that make more sense? Okay. All right, last question about this. The final part says, what is the concentration? As soon as you see the word concentration, what word should pop into your head? Molarity. Very good. So we're actually going to be, please guys, okay? We're going to be solving for molarity. And then they are actually courteous, and they ask you to give the units in this. Now, some of you are going to be like, I have no idea what this means. This is a new teaching point, just so you can recognize it. Anytime that you see the following, anytime you see that, what does anything to the negative first power mean? It's the inverse of, which technically means instead of writing it like this, they write it like that. Do you agree? It's the exact same thing. So anytime you see something to the negative first power, it means it's just on the bottom. Let me tell you why they do it this way. In a computer, is it pretty difficult to create a fraction? Yes, that's why they do it that way. It's all about them typing the questions out. That's the only reason you see it that way. You may even see this sometimes. You may even see what is it? That's latinum over mole. It's just, I'm telling you, it's just for them to type it. So if you see a -1, just put it on the bottom. Just put it on the bottom. Okay? All right. So they're asking it in moles per liter of the nitrate ion after the reaction reaches completion. Here's what I'm going to do. I'm going to show you the answer based upon the key. No. No. Hang on. Is that part 2? All right, here's what I want you to look at. This is the question. Notice what they've done. Please pay attention. It's not difficult. Don't let it confuse you. They've asked for the concentration. I need to pull this back up. They've asked for the concentration in moles per liter of the nitrate ion. Notice what it says, though. Please pay careful attention. It's the nitrate ion when? After the reaction reaches completion. Okay? Please notice the final concentration of nitrate, what? Must be the same as the... Why?
Equilibrium.
Kinda.
You can't have anything in the products that wasn't there in the reactants.
Conservation of mass. What you start with, you must end with. What you start with, you must end with. You agree with that? All right. So again, that's a new kind of thing. You're like, oh, I get that now. So the final must be equal to the very end. So here's what you can do. Do you agree they've given you moles of barium nitrate? They've given you that in the problem. Do y'all recognize this step? What do I call this thing? This is not the mole to mole thing I call. I call this the atom to molecule ratio. Why do I call this the atom to molecule ratio? Because in one barium nitrate, how many nitrates are there? 2. Does that make sense? Why are they going to nitrate specifically? Well, look what the question asked for. Let's pretend the question wasn't asking about nitrate. Let's pretend that the question was asking about the barium ion. Would your mole to mole ratio change? Would it change? In one barium nitrate, how many bariums are there? In one of these, how many bariums are there? 1. That's it. So does that not give you the number of moles? You agree? Moles of barium nitrate cancel, leaving you the moles of nitrate. Now, why can I not stop right there? What are they specifically asking you for? Molarity. So molarity is moles divided by liters. Do you have a volume in the question? What was the volume? Magical. Magical. That's not a lot of work. It's actually real simple. It's a mole to mole, and you divide it by 2. That's it. It's actually super simple. It's actually super simple. Okay? Jordan, ask a question. I can see it in your face. It's the very last question. Really?
Yeah, I think you should that's the key though.
This is the key. Yeah, the way yours looks is a little different. This is what yours looks like. Yeah, this is the key. I was showing you guys the key because sometimes it's easier for you to look at the key than to just look at my work. The reason I wanted to show you this is because, again, one more time, the nitrate in the beginning must be the same as the end because what you start with, you must end with. If you started with 0.6 moles of barium nitrate, you can go mole, atom to molecule, same thing as mole to mole, and determine. I'm going to actually change the question just a little bit. Hang on. Let me look. There's something I'm looking for. Oh, that's not what I want either. Come on. Give me what I need. All right, here's what I'm going to change the question to, and I want you to answer it. I'm going to kind of help. Matter of fact, watch this. I'm going to take all of this, and I'm going to actually... I'm going to change it to the hydrogen ion. All right, I'm going to help you. I'm going to get you started. Do you agree that the original concentration, let's try this again. What was the original concentration of phosphor, or the number of moles of phosphoric acid, please? 0. What? 300 moles of H3PO4. Convert that to molarity.
What was the answer to the last one we just did? Like the molarity?
The molarity was... I didn't even remember what the answer was. 0.60. 0.60 molarity. See if you can figure this one out. The only thing that's a change in this problem is what part? The ratio. The only thing that should change in this problem is the ratio. Now, of course, will the ratio affect your answer? Yes. Okay? But the ratio is going to change. You want to start? Okay.
Don't you just do like the atoms, moles?
Yeah. I'm in moles, and I need the number of moles of the hydrogen ion out of this thing.
Where's the hydrogen ion? At the end? So you gotta get the, trying to get the PO4 out.
All right, and one H3PO4s. How many H pluses do I have? There are 3 of them. It's asking specifically for H plus. Well, is H plus in H3PO4? It's just like a mole to mole, but instead of getting these numbers from the balanced equation, I get them from the compound formula. Works the same way. Does anybody have, that's 0.9, right? 0.900 moles of H plus. Why do I still have to divide it by 2? That's just moles. What did the question ask for? Molarity. So if I divide it by 2 liters, what did that give you the concentration of? 0. What? We're just going to say 0.45 molar. Hang on. Yeah, so 450. Sorry. Huh? 2 moles. For one H3PO4, how many H's are there? You did a mole to mole with coefficients. This is a atom to molecule ratio. I'm actually going to throw one more thing at you. No. It's real simple. I want to see how well you can do it. Let's see how many of you remember this. Does anybody remember what P stood for? P stands for what? All right, so just stop. Just chill out. Negative log. Please stop. Just watch. It's not difficult. Please stop. P is negative log. What do you think H stands for? Hydrogen ion. Do we have, what do brackets mean again? That's how you find the pH. Somebody, never mind, let me do it because you're just going to freak out if you have to do it. Negative log of 0.45. If you stuck your finger in that, would it burn?
No. Yeah. I had a 50-50 shot, yes.
What's the acid-base scale, Alex?
1 to 7, or 0 to 7.
0 to 14. Try that again. All right. Anything below 7 is an?
And it burns.
That will eat through your bone.
I was just like what they used in Breaking Bad.
All right. So again, that's just I wrote 4 things and taught you pH. All right. It doesn't matter. It's gonna be on the AP exam. Okay. But how hard was that? You took the negative log of the number you just found. He knew it. I taught y'all that. Parker. All right, so here's what I'm going to shift gears to, and we're almost done, guys. Let's work about 20 more minutes. Okay. Yes, ma'am. Yes. All right. This is the let me show you this. I showed you this. It looks like this. This is a hard copy. It's not on Notability.
Do we have that?
You should have it.
Wait, what is this?
I had it. 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 I had
Yep, that's it.
I was in there. Yeah.
Okay, yeah. All right. Again, special type of reactions such as metal carbonates. Does anybody remember what this will decompose into? It's going to be a metal oxide. Very good, Bryce. Metal oxide, and I'm telling you this now. Okay, plus CO2. In this particular example, please listen. In this example, what would your metal oxide be? Very good. Why BeO? Okay. First of all, beryllium's your metal, and they're both. It's the +2 and -2. So that would be your answer. Okay. Yes, sir. You got to keep trying. I can't help you on that one. Okay. Be able to compute the empirical formula given. Now, percent composition. If they give you percents, what do? Drop it, change it to grams. Please listen. What if they give you a missing percentage? If they say if it's tungsten oxide and tungsten is 44%, and they'll say anything about oxygen, subtract from 100. Okay. The other one, be able to calculate carbon and hydrogen from just CO2 and water. Y'all remember how to do this one? Okay, I'm just going to go ahead and show you. Let's pretend that it's 30.0 grams of CO2 and it's 18.0 grams of H2O. You might remember the mass of carbon dioxide? Okay, very good. Shut up. Shut up. Shut up. All right. Now, do you agree that I need grams of carbon from CO2? You know, I could go 1 mole and then 1 mole of CO2. In 1 mole of CO2, how many C's are there? 1. So I could go 1 and 1, and then 1 mole was 12.0 grams. So I can get rid of all the ones. Yes? So there are 12.01 grams of C in CO2. Yes, sir? Mm-hmm. All I did was skip all the ones. Okay. All right, last one. What's the mass of water? All right, Charles, let me actually show it to you this way. Out of the 44.01 grams, how much of it was because of carbon? To calculate the total mass of water, which was 18.02, how much of it was originally of the hydrogen? How did you know that? That's all I'm asking you to do. That's all I'm asking you to do. If you know that water is 18.02 grams, how much of that 18.02 was because of the hydrogens themselves? 2.02. That's all I'm asking you to do. That's it. That's how you get the mass of carbon, so grams of C, and that's going to be grams of H. You with me? Okay. What if I tell you that I have a compound that's made up of C, it's made up of H, it's made up of N, and it's made up of O? It's made up of those 4 things. And I tell you, I'm fixing to pour 6.92 grams of that thing into your hand. Okay, I'm just going to pour it in your hand. And I'm going to tell you that 28.6% of that 6.02 or 6.92 grams is nitrogen. How can you determine how many grams of nitrogen it was? Be very mindful of this. What do we know that a basic definition of percentage is? All right, so let's think for just a second. We know that part over whole is equal to what? The percentage. You agree? How much is the whole according to your data? All right, 6.92. What other piece of data do we have? 28.6%. What am I searching for? I'm searching for nitrogen. Isn't it the part? How do you do this mathematically? You multiply. You agree? Be very careful. Can I multiply these numbers exactly as is? This is a percentage, right? What would you do with that? Change it to what? Somebody tell me how much mass of the 6.29 would be nitrogen?
1.979.
That's how you do that. One more time, let's start over. I have a compound that has carbon, hydrogen, nitrogen, and oxygen in it, and I'm going to pour 6.92 grams of it in your hand. And I'm telling you that compound's made up of 28.6% nitrogen. Remember, please remember, this is all a percentage is. It's a part over a whole, and it's going to give you a percentage. Do you agree that I gave you the percentage? Do you also know the whole? This is 8th grade math. Don't overcomplicate it.
What's that called?
It's just percentage. It's percent composition. But you're basically working it backwards. Instead of me giving you the part and the whole, and I ask for percentage, I'm just asking for the other side of it this time. Okay? Yes, sir.
So you say part over whole, but the nitrogen 28.6 is part.
It's the percentage. It's
Oh, that's the
but 1.98 grams of 6.92 is 28%. That make sense? If I tell you there's 40 people in here and 6 just left, what percentage just left or remains? That's kind of, but this time I tell you 40, if I say 97% remained and there was 40 people in here originally, what part just left? You see what I'm saying? Instead of working with people, I'm just working it with chemistry. It's the same exact thing. All I did was just change your relationships. It's the same thing. 94% people remain. Out of 40 people that were originally here, how many people left the room? That's a simple. It boils down to that right there. Okay. All right. One of the things, and again, I just want to make sure, and again, guys, I'm looking at the test in front of me. No. Okay. This is something. Did you say airdrop? It's a sheet of paper. Okay. This is something that I also want to make sure that you are aware of to knowing how to do. Be able to determine the molar mass of a gas. Remember, this had the funny, cool little acronym name. This is not millimole. This is the molar mass kitty cat. All good cats put dirt over their pee. Here's how you'll know when to use this. What does D stand for? Not dirt. It stands for density. So, if they ask you for something with about a molar mass and you see a density, it's the dirt over P. Is it energy or gas R?
Gas.
Are you dealing with pressures? And I asked for a molar mass of a intelligent. It's in the question.
I was looking at my paper. Shut up. What are the others? All right, so it's .0821. What's the T? Would that be given in the problem?
Temperature. T and pressure. Yep. It's not millimole. You know what? It's funny y'all say that because I was working a problem the other day and the key worked it in millimoles and I wanted to scream. I was so upset about it. All right, know how to compute the molecular formula after finding the empirical. Do you know how to do this? No. All right, so let's look how to do this. Remember, it's the mass of the MF over the mass of the EF, and that is molecular formula, ladies and gentlemen. Thank you very much. I'm glad someone remembers that. They have to give you this number. It's the mass that you are given, and you actually have to come up with the bottom number. Now, this is going to give you a specific whole number. Once you find that number, do you circle that and say, here's my answer? What do you do with that whole number? By the to the subscripts. Multiply it to the subscripts. Multiply it to the subscripts.
I don't.
Starting to get a little better feeling? A little bit. A little bit.
No.
Not really. I wasn't here then.
What do you get paper out?
I wasn't here. I just walked in like 5 minutes ago.
Yes, sir.
Okay, so Latham over mold.
Yes, sir.
We've already talked about this, but that, what does that go with? What is that? I'm talking about like what? How do you know when to write Latham over mold?
That is the unit for R.
Unit for.
What is the unit for grams? Let me try that again. What is the unit for mass? What is the unit for volume?
Liters.
What is the unit for temperature?
ATMs. No, temperature is Kelvin.
The unit for pressure.
ATMs.
The unit for R. Latham over Molk.
All right, got it.
Okay. All right. So, please, this is really important, guys. I've covered this in another part of the series. Calculate the mass and moles of water and the compound from a gravimetric hydrate lab. Here's what's going to happen. I'm going to take a compound that's got a hydrate in it, and I'm going to burn that thing. Okay? I'm going to burn it, and then I'm going to mass it. I'm going to burn it again, and I'm going to mass it again. Why did I burn it for the second time and weigh it for the second time? Make sure what? All the water is gone. What if I want to make precisely sure?
Burn it again.
Burn it again. How will I know after I burn and burn and burn when all of the water has officially disappeared?
Same math.
When the masses stop changing. What happens for some reason if the mass goes up by 1/1000th?
You just burn the
Say it again.
anhydrate.
Say it
You just burn
again.
the anhydrate.
Use the lowest amount. Use the lowest amount. Now remember, the mass that you're going to get also includes the container that it's in. Do you use that as your total amount to go grams to moles with? Why? Because that crucible has no effect on that compound. Please be mindful of that. Okay? All right. You should be able to know. You should know how to determine the another one. Determine the formula of a hydrate. Do y'all remember how to do that? All right, just in case. Remember, it's the moles of the H2O and what? Divided by the moles of the, very good, anhydrate. That's going to give you a number. What is that number? That is the number of waters specifically in the hydrate. That is the number of molecules of water in the hydrate. You guys are acting. You guys, I know you're stressed out, but I guarantee you are far, far much more along than students in the past that I've had in AP. Guarantee it. I promise. Everybody is. It is a lot, and you're not used to it. It is a whole lot, and you're not used to it. And I've been begging you guys got to study. This is not a class you can study tonight and be prepared tomorrow. It's not. Yes, sir.
What about like
You will. What did he say?
I've been studying the whole.
Yeah.
classic?
Wow, y'all are gross. Yeah.
Ew.
Okay, I'll watch it.
It's been a good one today. You guys have missed a good one.
Yeah, we had to work out.
Clearly.
Clearly. Or y'all been playing in the mud puddles. Okay. All right. Explain how the following could affect the hydrate formula. So let's talk about this, and we're going to try to do one of these labs here soon. Too much heating. What if you heat it too much? You're going to burn the product. Do you think there is a possibility that you could actually add some of the atmospheric gases into the product? There's a chance for that. If you just continuously let it burn, it may actually form what we call nitrides. And what would that mean actually physically happened? Nitrides.
Ashes.
The nitrogen in the air bonds with the compound in the crucible. Nitride. Why would it be nitride and more than likely not an oxide? What is the percentage of nitrogen in the air? It's like 70%. What's wrong with that? I would hope you would know that.
Know what?
That nitrogen is the highest percentage of gas in the air?
It is.
All right. What if you did not heat it enough? You still got water in it, so please listen. You still got some water. So if there's still water, is that going to increase your mass of water?
Yes.
Yes. Will that increase your mass of hydrate? Yes. Will that increase your moles of both?
Yes.
Will that increase your number of waters?
Yes.
Be careful. The last one, what if you splattered some of it out? What if you weren't careful and you knocked some of it out? Are you sure about that? Means you have lost. Not only have you lost some of the water, what else have you lost? Some of the anhydrate as well. So your number of moles will decrease, correct? Will that decrease the number of waters you could possibly have? Yes, be careful.
We ever gonna do a lab like
Yeah.
so?
Yeah, right now. We're going to do it right now. No. The loose bottle, no. We'll do it, not right now.
Come on, we have nothing else to do.
Before you leave. All right, be able to calculate the relative atomic mass. Now, notice what I have just swapped to. I've swapped colors. I'm now on the multiple choice part. Guys, I'm telling you right now, tomorrow when you get on the test, you're going to think the multiple choice is harder because you're going to have to put, in terms of effort, a little bit more think time in. Let me give you this, if I can give you any words of advice. Guys, I've sat down and I've worked all these problems twice. If you don't see a balanced equation, write a balanced equation tomorrow, because that's the only way you're going to be successful. It's because it's going to give you one compound and it's going to want to go to a completely different one. And the only way you're going to be able to do that is mole to mole. And if you don't have a balanced equation, you're not going to be able to do it. Please, balanced equations, write them. You're not going to see them. You're going to have to come up with them on your own. Be able to calculate the empirical formula for percent composition. Guys, I'm going to be honest with you. This multiple choice test, some of them are a little and that's why I'm going to give you this use. These questions are designed to be able to be done without a calculator. They're designed. I give you 22 grams of carbon dioxide, and I want to know how many moles that is. What is the molar mass of carbon dioxide? What is 22 divided by 44? They're designed to be able to be done mathematically without a calculator. Now, no. It's more of right now, I want you guys to feel confident in your abilities. But at the same time you're doing it, I want you to be able to say, oh, I didn't even need a calculator for that. I can see that would be 0.5. And then what if it's 44 and then I'm doing a mole to mole conversion, and let's just say the mole to mole conversion is 2/1. What's 0.5 times 2? 1. You don't need a calculator for that. You guys have just gotten so used to, oh my gosh, a stoichiometry in chemistry. I need a calculator to plug this in. It's designed for it to be simple. Now, some of them are a little higher order thinking than I'm ready for you to do now. So that's why I'm giving you the perks of having the calculator. But when you write it down, see if you can do it in your head. And then plug it in the calculator just to give you some safety net. Just see if you can take 2 seconds to say, all right, I get it all. Okay? Whatever you need to be able to do. Here's the big one. Determine the mass of the element from the mass spec. How can you determine the mass? The percent abundance. Which one will be closest to the actual mass? The highest peak. Right? The highest peak. Okay? Determine the percent abundance of an isotope based on specific isotopes in the element. This is how you will do that. if it says determine the percent abundance of an isotope based on the specific isotopes of the element. You take the mass of the first isotope, multiply it by its percent, and add it to the mass and the percent of the second one. And what does the ... mean? How many of them there are? If there's 4 of them, just do it for 4 of them. The only thing I need you to be aware of, can you take the percent abundance and plug it right in? No, why not? It's got to change it to a decimal. Be very careful of that. Okay. What? It'll be on a table. It'll be on a table, yes. It will be on a table.
So it's out of 100, so all you have to do is drop the percent.
Essentially. The what? Okay. All right. Another thing. What if, let's say that you should be able to do this, but I'm just going to give an example. Carbon 12, carbon 13, carbon 14. The total mass percent of this one is 98. This is like 1. And here's my question mark. Okay. You know what? Never mind. Ignore that. Ignore that. Completely ignore that. Completely ignore that. My bad. Yeah, yeah. Know how to find any variable of molarity when given the other two. Okay. Again, if you want to help with this one, the way that you can do this is the triangle. Remember, it's molarity equals moles over liters. Guys, that's going to help you. It's going to help you. What if they give you grams and volume? What do you have to do before you find molarity? Convert it to moles first. Determine the amount of reactants needed to complete a reaction based on particulate representations. It's all about pictures. So, let me show you a picture. Chandler, you worked on some of these earlier. Did they make sense?
Yes, sir.
All right, good deal. So let's look at one of them. This learnerator thing, I have no idea what was going on with that last night. I appreciate some of you. It actually works, by the way. If you look at the code, it's W capital I, not W18.
Well, I copied and pasted.
And that's, I don't know why it didn't work. If you go figure, right when I need it, it's not going to want to work. Pause the video. Forward again. All right, this is a particulate representation. You can barely see it, so I'm going to add it. But there are 2 colored dots right there, and there are 2 more right here. The first thing I want to make note of, do you agree that this is a reactant plus a reactant, and this yields this product? When it sank to the bottom, what do you think that means happened? It became a solid. Do you agree with that? Very good. So you've got to figure out what this black thing is and what that clear thing is. Why the black and the clear? Because that's what reacted to form the solid. Those of you that remember this, the things that continue to float, that did not react, that are watching, what do we call those? They're hanging out watching, they're cheering it on. Spectator ions.
Yeah.
Is that really what they call them?
Yeah. The ones that are floating around still that don't form solids are spectator ions. All right, so you're going to learn this later when we get to solubility rules, but you're going to want to know, and actually some of you already remember this, and I told you the 2 main things you need to know about solubility rules. Number 1 was all group 1s are what?
Soluble.
Which means they will never form a solid. Do you agree? A, is K and Na, are they both group 1s? So will that either of those 2 ever form a solid? Guess what? A's wrong. Okay? So we can go ahead and say, guess what? A, we know you're wrong. All right? I'm just going to skip down to D. What state of matter is O2 in? It's just O2. What is O2 in? Do you see a gas anywhere on there? Wrong. Okay? Now, the next thing. We can look at this one and this one and this one and this one. So let's look at C real quick. Na is a group 1, right? So do you agree that dissolves? But let's look at CaCl2. Does anybody remember that special rule about the chloride? It's soluble unless with who? Heavy metal bad guys. Who are those three guys? Silver. Okay. Silver, mercury, and lead. Is calcium either one of those three? So that's going to fall apart. Now, NaNO3. That's the group 1, so it goes away. What about Ag? That's a heavy metal bad guy. So what is that thing going to turn into? It's going to turn into a solid. So that is your answer. That is a particulate representation. Yes, sir.
Will it be like that?
Mhm.
Is that like
Almost. Kind of.
like, or would it be like the molecule pictures that we got?
It'll be more like those pictures. Yeah. Okay?
No color, right?
Yeah, no color. All right, let's see. There's one more that I wanted to show you. I think it's this one. Maybe, maybe not. I don't remember which one it is.
I said it even. Oh, they're not funny. Oh, I know.
All right, let's look at this one, guys, real quick. I promise we're almost done.
You get to do like a little hookah bottle, couldn't you? The flaming bottle.
I'm out of time.
No.
Now, this question's a little bit easier. Again, you can't really see it, but there are two little gray dots right here, and that's what. Shoot, I can't even tell because it's so faded. The white dots are C. Two aqueous solutions are mixed in a chemical reaction. The substances in this beaker represent the products of the chemical reaction. Which substances in the particulate level diagram is a spectator ion, which means they do not form solids. So which two can we knock out that are not solids? The black and white, which means B and C are out, which means A and D are floating. So the correct answer there is A. That was easy. Okay. This is the last particulate that I want you to see, I think. I hope this is it.
Can you go over percent UO2?
Actual over theoretical.
Yeah, but how do you get the actual? I mean, theoretical. How do you get theoretical?
You have to solve for that using stoichiometry.
Actual
All right, that perfect. This is what I want you to see. Wink, wink, hint, hint. You need to pay attention to this one. You need to pay attention to something like this. Here is the particular reaction. It's 4 aluminums plus 3 oxygens makes 2 aluminum oxides. Okay? So for every 4 aluminums and 3 oxygens, you get 2 aluminum oxides. Each particulate level diagram represents an initial. What does it mean by initial? It's very beginning. It's your reactants. Each molecule represents a mole of reactants. That's very important. So for every 1 blue dot, that's 1 aluminum. How did I know that the dark blue was aluminum and not the 2 lighter blues? Do you see that? The oxygen's diatomics. There's going to be 2 little dots stuck together. So in A, how many aluminums do we have? 1, 2, 3, 4, 5. So we've got 5 ALs and how many O2s? All right, we've got 4 O2s. Very good. All right, and this one, we've got 3 ALs and 1, 2, 3, 4, 5. 5 O2s. This one, 1, 2, 3, 4, 5, 6, 7 ALs and 3 aluminums. And then 4 aluminums and 2. No, I didn't. No, I didn't.
302.
My bad. Okay, that's O2. I just messed up the formula. All right. So the question is, which initial mixture produces the most product? If we know it's a 4-to-3 ratio, which one can we automatically kick out?
4 to 2.
I say the last one. Why? Here's why. If you need 3 oxygens and you only have 2, are you even going to make one of these things? You're not even going to make one of those. So that's got to go away. You with me so far? Now, I may even get rid of this one too. Why? That's only going to make 1 for sure, and I know these 2 can make a little more. Do you agree? So that one's got to go away. Now this is when it kind of gets a little tricky.
Wait, Mr. Richardson,
Very good, Charles. You need 4 aluminums, and so that one goes away. Very good. Very good. So that automatically leaves you with what? Got to be A.
Hold up, Richard.
No, and I'm so glad you just said that. I want you to take this class and learn. What's wrong?
I just love it that I hear laughter and clapping in a after-school.
All right. So the whole point is, and what he said is what I want to point out. I want you to take this test using process of elimination. It's the only way you're going to be successful. The only way. Guys, instead of having a 25% chance, knock out 2 of them and get to 50-50. You've said that 100 times. Get yourself to 50-50. You should automatically know that this one's never going to work. This one right here, because there's not even enough oxygens to even make a product. You should know that's not going to work because there's not even enough aluminums to make something. And here, you're going to get more out of this one. Again, so really these are the only 2 that you can compare. But you don't have enough aluminums to overcome. Okay? Yes, sir.
I don't get wouldn't it still kind of be the same? Because in that one you can only make 1 reaction, but in the other one you can only make 1 reaction.
Hang on one second. If it'll hurry up. All right, here's the explanation. Use the mole ratios to determine the answer. Each molecule represents a mole of reaction according to the balanced equation 4-3 to produce 2 moles of product. Okay? In box A, the initial mixture has 5 moles of aluminum and 4 moles of oxygen. 5 aluminum can produce 2.5 moles of product. You with me? Okay? 4 moles of oxygen can produce 2.6 moles of product. All you did was a mole to mole ratio. Okay? Aluminum will run out first and only 2.5 moles of product will be produced. So essentially you're finding the limiting reactant. All other boxes will produce 2 moles of product. So if you just compare mole to mole, sometimes you can visibly do it and sometimes you can't see it the other way. The way that I would probably kind of do this personally is I would make circles around it. All right, so I need do you agree that that's going to make 1 product? 1, 2, 3, 4 aluminums. 1, 2, 3. Right? Over here, 1, 2, 3. Let's try this. Come on. Please work. This is the last thing I want to do. 4 aluminums and 3 oxygens. Notice what you have left right here. Do you agree that you kind of have partial of a product? But over here, you have no oxygens left to even try to make a reaction. So does that kind of make a little bit more sense? Okay. All right, guys, that's it. We're done. Y'all have a good night.